Hey.
It's the one, the only Usher's movie. Oh my God, it's so sponsored by Citrus.
Good Morning America is sponsored by Dirty X.
Back now with Soul Powerhouse Legacy, she just performed Stone off her new album, The Wild Card. We want to welcome her now here to GMA. And Legacy, we've all been talking about that song, Stone. What a great song. And we've learned that you actually recorded the album, most of the album, pre-pandemic, but you had to record the last two songs during the pandemic. You didn't have the equipment or the studios. You had to order it on Amazon and build it and then record the songs?
Yes. Do you?
Okay, let's get started. It's 9 o'clock. As a reminder, video cameras are required for lecture and lab. I'm going to share my screen. We left off talking about model checking. So the idea here is, just to recap, we have fit a simple linear regression model. Using R, we use the LM function. We have a response variable and a predictor variable that we give the LM function as arguments in R. We execute the command and we get our parameter estimates for beta 0, beta 1, and sigma squared. Now, no matter what we put in there, as long as it's allowable by R, it's going to give us some value back. It's going to give us those three parameter estimates back. And the question is, do those estimates, are those a good, do those estimates actually reflect what the population is doing? So we were talking about the elk data before, and we have our data, and we got this model output back from our studio, and R is going to give us a line no matter what, no matter how appropriate simple linear regression model is for the elk data, whether it's appropriate or not. And it's up to us to check the appropriateness of this model for the data that we're dealing with. And that's what model checking is all about, to make sure that the model that we're using can actually produce data that look like the data we observe. Because we're going to use this model to make inference on the population, and inference being we're going to say something about the population. And if we're going to tell a newspaper outlet or something what's going on, we better be sure that the model that we're using is a good model for our data. And to check that, we have to check the model assumptions, and that's what model checking is about. So we can fit almost any model to any data set. The question is the model good for the data set? Here are the assumptions of simple linear regression and multiple linear regression. So we're going to go into multiple linear regression today, and we'll talk about these. There's 3 assumptions. Those are independence, that the observations are independent of each other. We've talked about these with the ELK data and how these data might violate that assumption, because our current year's data are going to depend on last year's data. Normality, we talked about the residuals being normally distributed. We say that in our model statement, right? Go back to the first one here, right here. Even if I go back to let me write out this model statement. When we say yi equals beta 0 plus beta 1 xi plus our epsilons, we say our residuals, epsilons, come from a normal distribution with mean 0 and variance sigma squared. So this part right here is that second model assumption of linear regression. And then homoscedasticity, that the variance of the residuals is the same for any value of x. So the variability in our data don't increase or decrease as we increase the values of x. So for the ELK example, what that means is as the years increase from 2005 to 2019, the data don't get more and more spread out. And let me show an example of what this looks like on the whiteboard. So if we have x equals year on the bottom down here, and y equals our ELK counts, the assumption is when we look at the residuals, this is 0. The spread stays about the same about in the same area, no matter what value of x we have. So let me show an example where that assumption is violated. Let's say the ELK data actually looked like this. What is shown here is that the variability in the data is kind of fanning out like that. It's increasing. So when we were talking about what sigma squared means, sigma squared kind of controlled the distance from the line here, from the fitted line, or sigma we were talking about. Sigma controlled the fitted line. And if we thought about sigma for each of these examples, sigma here would be big. And down here, sigma would be small. So we're assuming just one sigma value for simple linear regression. So that same value has to control the spread of the data for our entire time series, for our entire values of x, all of our years. So it has to look, the data have to look more like this. And if it looks like this, the violation is, the assumptions are violated. So that's the assumption of homoscedasticity. All right. There is an easy way to check these three assumptions in R, and we can do it visually by looking at plots. So the command for this, I'll go through an example when we move to multiple linear regression. But actually, the command for this is just plot. If we create our fitted model, we say, let me go back to and write this down. We create our fitted model by saying, let's say, model fit. This is R code now. LM y tilde x. Now we've created an object here called model fit that stores all of our fitted model results. If we do this command, plot model fit, it'll give us three plots that are going to examine those three assumptions of simple and multiple linear regression. So it's just one command, and this command here is going to give us the next three plots that I'm going to show. All right, here's the first one. Are the residuals independent of each other? What we're looking for in this plot is that this red line should be pretty straight and follow 0. Now, when we only have 15 or so data points, there's going to be some movement of this red line in here. But what we don't want to see is what we see here. We see how there's a clear trend in the data. It starts up high, and this would be above our fitted line. It goes down. These are values below our fitted line, and then it goes back up. So this is a clear violation of our assumption of independent residuals. And this is kind of what we've already touched on. We expect this because elk populations the size of the population 1 year depends on what the population was in the previous year. We can see that if we write out the BIDE model. Why does it depend on the previous population? Well, let's look at our basic model of population ecology. You've seen the BIDE model in previous classes, in Kelly Stewart's class and Kevin Shoemaker's class, where you have the population at size t plus 1 equals the population size at t plus the number of births during time t plus immigrants at time t, minus the deaths at time t, and then minus the immigrants at time t. So in our basic model of population size, we see that our current population depends on our last year's population. So we expect there to be some correlation in the residuals, and this is why maybe simple linear regression would not be such a great model for the elk data. So eventually we're going to need to build complexity into our model to build in the realism that we have, but we're starting with a basic building block of simple linear regression. So if we see a plot like this, then we can say there's a violation of this independence assumption, and we would want to explore alternative models. All right, the next assumption. This is the second plot. Are the residuals normally distributed? If they are, these points should follow along the line. And it actually looks like most of the points follow along this line pretty well. They're pretty close to this line. There's two exceptions, 8 and data point 8 and data point 14. Those ones are really the outliers. We would call these outliers in our data. Let's take a look at what points these actually are. So I explored this beforehand to see which points they were. And the points that these are, here is 14. It's this data point. It's the highest count. And the 8th count is right here, the lowest count. So these 2 points are really violating the assumption of this normal distribution of the errors. These would be considered outliers. So in addition to checking our model assumptions, this plot also allows us to find which data points are outliers.
Hey, Professor, there's some people in the waiting room.
Okay. Julie, can you let those people in?
I don't think you have me as a co-host, so I can't even see the waiting room. Like,
Oh,
I didn't
okay, let me,
see people in there.
yeah, let me do that. Okay, and then I'm gonna make Julie co-host. Keeps moving around. Okay, Julie should be able to let people in now. All right, so 8 and 14 are outliers in this data, and because of those 2 data points, it doesn't appear that the residuals are normally distributed. Although, honestly, this plot doesn't look too bad. I wouldn't be too worried about this plot. Most of these points here are pretty close to this line, except for these 2 points, and we often see that with our data. Are the residuals homoscedastic? Do they have that even spread around our trend line for the entire range of the data? So what we're looking for here is a plot that has a straight red line here. This is pretty good. This isn't too bad. This 0.14 brings this line up a little bit, but I wouldn't be worried about this line here.
Sorry, Perry, did you let those people in? Because I'm still not seeing. Okay.
I
just want to make sure.
Yep. Okay. So this is that third assumption, are the residuals homoscedastic? And I would say, looking at this, they're not too bad. And there will be more examples of data that you can examine these trends, examine these assumptions in some of the practice problems. Also, there is tons of information on examining residuals online. If you just Google, how do I examine the assumptions of simple linear regression, you'll get pages and pages of information on how to do that. It's one of the basic questions in an introductory statistics course. All right, so last slide here. Why is it important to meet these model assumptions? Why do we have to check our model assumptions? It's because we are using our model fit to our data to make inference, to say something about the population. All of our inference assumes that the model is, quote, correct, unquote. And I put correct in quotes here because, as I mentioned in the lab, that all models are wrong, but there are some that are useful, and we take that assumption, or we take that statement pretty seriously in wildlife ecology. So we want at least a useful model, but our inference does assume that the model is correct. We assume the data we observed were generated by some underlying model. And the question is, could the data we observed have been generated by the model we chose? If we were going to take the parameters that we estimated, plug those into the R norm function in R, and simulate data, are those data going to at least look like the data we observed in nature? If they do, it seems like our model's okay. But if there's something different with the data compared to the model that can be simulated with our model, then we might want to consider a different model. If the model we chose cannot generate the data we observed, then we need a different model. This is what I just said. And the last thing I'll say about model checking is we can't use model checking to identify good models. However, we can use model checking to identify bad models. So a model can be good based just by coincidence. And we'll never be able to use model checking to identify that. However, we can observe when models are egregiously wrong, and that allows us to throw out those models and think of new ones. Okay, so here's our simple linear regression model with the data set we've been talking about for all of these. And the question is this a good model? We've kind of touched on this quite a bit, that no, maybe this isn't a good model and we need something else. And that's where we're going to go with our next lecture. We're going to build in model complexity to the simple linear regression model. But everything we've learned about the simple linear regression model is going to translate directly over to our next chapter here. All right, before I switch to multiple linear regression models, are there any questions?
I have a question.
Yes, please.
If any one of those three things that you mentioned, if any one of those aren't met, does that essentially mean we'd have to try a different model, or
Yeah.
Okay.
Yeah, it does. And there are ways to tailor the simple linear regression model to help alleviate any one of those three different assumptions.
Okay, cool.
So if we violate the first, the independence assumption, we can build in a time series component to that model to help with that independence. So we have a lot of times, there's a whole statistical field of time series analysis that deals with data that are correlated in time. If there's not homoscedastic errors, we can allow sigma squared to vary through time so that we can account for that. Anyway, we can look at those three assumptions, see which assumption is violated, and proceed accordingly. Good question.
All right, thanks. And then follow up, what would be a good example of when we would use this model in population dynamics?
When would we use simple linear regression model?
Yeah, so when would it be a good idea, since obviously the elk data didn't really work out for us?
Yeah, so I've touched on one example where it worked out okay, and that was looking at the home range size. I just touched on this example briefly, looking at the home range size of spotted owls relationship with relationship to heterogeneity. So the example was this, I'll just to refresh everyone's memory. We had home range size, we had patching, number of patches. And we had home range size of spotted owls. So the data were collected by putting radio transmitters on spotted owls, following them around for an entire summer, and then looking at what their home range was, defined as by just drawing a line around all the points they use, and then counting the number of patches within their home range size. And the data looks something like this. And we fit a simple linear regression model to it. And the model assumptions held. There was no evidence for violation of model assumptions. So we made inference on this relationship here. And the inference was, as the number of patches increase, the home range size increases. And what we speculated based on this relationship was that as fragmentation within a home range increases, the habitat becomes less suitable, and owls have to cover larger areas to obtain the resources they need to survive and reproduce. So that was an assumption where simple linear regression was an okay model for the question we were asking.
Thank you so much.
Yeah. Any other questions? Okay, let's move on to the next lecture here. This is multiple linear regression. Simple linear regression, we had a response variable and one predictor variable. All we're going to do for this extension is we're going to allow more than one predictor variable. Let me check and see if it's in the waiting room here. Actually, Julie, you can do that, all right? Okay, so multiple linear regression just means we have multiple covariates. In our previous example, we had y equals beta 0 plus beta 1 x. Now we're going to have y equals beta 0 plus beta 1 x plus beta 2 x2 for as many covariates as we want. Okay, here's an example. This is avian species richness in the US. Now let's just take a brief break from the numbers here and identify these bird species. So let's see, we have 1, 2, 3, 4, 5, 6, 7 species. Anybody know top left species?
Green-winged teal.
Green-winged teal. I'm going to put this on speaker view too so I can see who's some participation points here. Okay, green-winged teal. I missed who said that.
It was me.
I still didn't see it. Let me see if I can get to speaker view. I don't know if I can do speaker view. There we go. James, was it James? That's who I see right now. Okay, it was James. All right, how about the top right? What do we have? This one's a little more challenging.
Is that a black oyster catcher?
That's right. Is that Richard?
Yeah.
Okay, yep, black oyster catcher. How about middle left?
Blue heron?
Yep, GBH, great blue heron. And in the middle?
Northern pintail.
Yep, northern pintail. I have a graduate student working on northern spatiotemporal statistics related to northern pintails in the US and Canada. How about on the right? Middle right.
It's a barred owl.
Barred owl, right? Becky. And then bottom left?
Wood duck. Wood duck.
Wood duck, yep. I also have a graduate student working on wood duck and mercury in Fallon. And then bottom right.
Is that a short-eared owl?
Yep, short-eared owl. All right, so the idea with this example is how many species are in each state? And can we explain that by covariates in the state? So let's look at an example. So the response variable for this example is the number of species observed in each state over some period of time. I don't remember the exact period of time, but it's over some time because when we're describing populations, again, we want to describe where and when we're talking about. So this is in the US and Puerto Rico, and then I think it was over 1 year, observation over 1 year or maybe one breeding season. I'd have to go back and look up exactly what that was. And we want to know if the number of species in each state is related to 3 different covariates. And those covariates are temperature, the area of the state, and the amount of precipitation. So can we explain species by these 3 X values? So we have X1 is temperature, X2 is area, X3 is precipitation. Those I might revisit those orderings. Okay, so we see Texas, it looks like, has the most species of all here. Nevada, we're on the lower end for species. California has a lot of species. Arizona's pretty good. New Mexico's pretty good. Okay, not shown as Hawaii, but Hawaii is included in the data, and in fact, Hawaii has the fewest species of all the states. Here are the learning outcomes of this lecture. We want to be able to understand how multiple linear regression is an extension of simple linear regression, and when we would apply multiple linear regression versus simple linear regression. And the answer to that is simple. It's when we have more than one covariate we're interested in. Number 2 is understand how what we've learned about simple linear regression applies to multiple linear regression, and that includes things like writing out our model statements, both the fitted model statement and the general model statement, how to fit these models in R, and it's an easy extension in R to do that. Interpreting model parameters, it's very similar to what we saw before. And then model checking again. Do we have a good model? Lastly, we want to know how polynomials can be used in multiple linear regression to make models more flexible. So let me just give an example of a polynomial here. in calculus, we've seen the function something like y equals a plus bx plus cx squared. Actually, in algebra, we may have seen this too. And we can continue writing this as much for as many orders as we want. So we can say y equals a plus bx plus c x squared plus dx to the third. This is a polynomial where we have the same covariate. We just raise it to the power. And what this does is allow us to draw a more flexible line. So when we have y equals a plus bx, the resulting function is a line. When we have y equals a plus bx plus cx squared, the resulting function is a polynomial like that. And depending on which ones of these a's, b's, and c's are positive and negative, it can either be upside or down, or right side up or upside down. It can be over here, it can be up here, and so on. We can fit these functions to the data. If we had three-level polynomial, y plus bx plus cx squared plus dx to the third, it gives us even more flexibility and gives us a line something like that. So now we can see where maybe this would, something like this would be useful for the out data where we had ups and downs, and we wanted to track that population a little more closely than we were able to with just a straight line. All right. Okay, so multiple linear regression. When we had simple linear regression, we had yi equals just this part plus epsilon I. And remember, I from 1 to n is just the rows in our data, in our Excel table. It's which row the data were stored in. And we just use that to help us keep track of to remember these are talking about data points in a row. And we had EI, the epsilon I is normal with mean 0 and variance sigma squared. Now all we're doing is adding extra covariates at the same time as our other covariate. And we could add as many covariates as we want. So if we were looking at avian species richness, we would have beta 0 plus beta 1 x1, where maybe x1 is the area of the state. And now we have beta 2 plus x2, where x2 is the temperature in the state. And then if we had beta 3 plus x3, and where x3 is the precipitation in the state. And just like simple linear regression, yi are our data. These are the number of species we have. x1 are our covariates, so we have this information too. We have the information on the area of each state. x2 is the temperature in the state. We have information on average temperature. And then x3, this says xd, but let's say that d equals 3. That's the average precipitation in the state. So we have information on y1, x1, x2, and x3. We could imagine an Excel table where the first column is our counts of species. Our second column is the area in the state that those come from. Our third column is the temperature, and then our fourth column is precipitation. What we don't know, just like in simple linear regression, is what these beta values are. And we're going to use R to estimate all of the beta values that these have. Same with sigma squared. We don't know what sigma squared is. All right, any questions about this? Now, when we plot simple linear regression, say mu I equals beta 0 plus beta 1 x I. That gave us, that's the equation of a line, where we have our data yi. We could also put mu I, say yi or mu I here. And then x is down here. And that gave us the equation of a line. And that line told us the relationship between x and y. What we're doing when we add more than one covariate is we're adding another dimension to this graphical plot. So here we still have, let's say, yi on this axis. But now we have x1 down here and x2 down here. And the equation, mu I equals beta 0 plus beta 1 x1 plus beta 2 x2 is actually the equation of a plane. It's not the equation of a line. Because for each data point, let's say there's a data point, right, coming up, we look at one state. Let's say it's Texas. So Texas has a huge area, but let's say this is area, and this equals precipitation. If we find the value for Texas, it has a big area, not very much precipitation. And the number of birds is going to be a point that's kind of floating in space here. So we're going to have a cloud of points, a three-dimensional cloud of points, not just a one-dimensional set of points that we did when we had simple linear regression. And we're trying to fit a plane. See if I can draw this okay. Trying to fit a plane through these x coordinates. And that's what mu I is going to be. It's going to have as many dimensions as we have covariates. Now we can only really draw this when we have two covariates. When we have three covariates, it becomes too hard to visually see. We would need to add another dimension like time in there to spin it around or something. But when we have two covariates, we can visualize this as a three-dimensional plane. And then the question is, which beta parameters best fit those data? And although it's hard to visualize with more than two covariates, R is going to be able to estimate that stuff. So we're going to use R to estimate that. So if we have two covariates, let's say area and temperature, we're trying to figure out which plane here best fits our cloud of points in our data. Now, really, with the example for species richness, avian species richness, we have three dimensions, but we can't visualize that easily. Now, what are those parameters? How do those parameters relate to here? Beta 0 is still the intercept here. It's when area equals 0 and temperature equals 0. Where does this value cross the y-axis? So here's our beta 0. Let's say area is x1. Beta 1 is going to be the slope going this way. We're seeing the slope going this way is changing a little slower than the slope for temperature. So beta 2 is the slope for temperature. That's what's moving the quickest. It's going up and down. It's like there's 10 different changes in slope for temperature for each change in area. So it's iterating over all of these changes. And what we're trying to do is figure out what the values of beta 0, beta 1, and beta 2 are that best fit this plane here. How do we estimate the parameters? Well, we use the LM function in R. Same thing we did before. The only difference now is we have our response variable y. We just add a plus our additional covariates we're interested in. So let me go to R and actually do this. Okay, I'm going to clear this and clear this. This little broom clears everything in your R environment and all your plots. All right, let's, is there a question? Okay, let's review a little bit of our code here. Here's question 1 to lab 2. How do we load in data? Well, first we have to tell it where it's stored. This is where I stored the avian species richness data on my machine. It's in this path here. So I'm going to set the working directory. Set working directory tells the folder that R is going to look at automatically. Read.csv reads a CSV file. The CSV for the birds is here. And actually, why don't I just pull that up to show you what the data actually look like. Birds is in lab 2 here. Here are what the data actually look like. Rank is the rank of species that, I don't know what rank is. That's something someone has in there. I received this data set as an email from someone. Sometimes they have columns in there that we don't always need. But here's what we have. We have state abbreviation, the number of species. This is our Y variable. The area, and this is in square kilometers, I believe. The average temperature, the average precipitation. So here's our 3 covariates. We have X1, X2, and X3. And here's our Y response. So these are the columns we're going to need. I'm going to load this CSV file into R using the read.csv function. So this is lab 2, question 1. How do we do this? We can use this read.csv function. We put the name of the file, including the extension, in quotes. We look at that. And in teaching all the R workshops I've done, it seems like this is one of the hardest things to do, to actually read the data into RStudio. So if this is challenging, hang in there, because it's challenging for a lot of people to actually just get the data into RStudio. Very common issue people have. We can look at the first 6 rows of our data by doing this head command, head data. And it shows us the first 6 rows. We've stored this as a data frame. We talked about matrices and data frames. With this one, we have lots of names and numbers in here, so we can store it as a data frame. Let's actually say, is data frame data true? So we know it's a data frame, not a matrix. Here's something new. Let's see, here's something new that we haven't done, this which command, and we can use which to find something that we're interested in. And we want to know which data rank equals 1. And that is 44. So the 44th row is the one that has the most species. So I mentioned before I didn't know what rank was. I actually do know what rank was. That's related to species. And that is Texas here. Okay, so now we can say, we can subset our vector. We can say data state name, create a vector, and then subset it to the 44th one to see which state is actually ranked first, and that is Texas. You can also say which one's ranked last, and that is Hawaii. So Texas has the most species during this time period, and Hawaii had the least species. Hawaii actually has a lot of invasive species, and their native bird population has been decimated. All right, we can create vectors. We did this in lab 1. Here's why we might want to do this. Let's subset the column for species and call that Y. And then let's subset the 3 different covariates we're interested in. Area, temp, and precip. Area is going to be X1, temp is going to be X2, and precip is going to be X3. So we're just creating vectors. We can look at what each of those look like just by running Y. There's our list of 51 variables, because it's all the states, including Puerto Rico. Then we have X1, X2, and X3. Now here's what we're interested in. we want to use this LM function to fit a multiple linear regression model. And the only difference from multiple linear regression to simple linear regression is this little addition here, where we can add additional covariates. So we have X2 and X3. So let's fit that model. We can use the same summary command we use for linear regression models. And that gives us our output. So here is our output. Intercept. This is our beta 0 value. And we'll talk about interpretation of this. X1, X2, and X3. And this is the output we're going to get. Our objective is to interpret this output and say something about the response variable. How many birds are in each state? And is that related to our 3 covariates? We see what our standard error is down here. Our standard deviation, sigma, 45.41. All right, let's go back to our slides. Here's that same output we had. Here's a good reference slide if you're looking at this output in the future and you want to see what each of these are. What does this analysis mean? Here's the interpretation and how this extends to multiple linear regression. The intercept. The intercept is the expected number of species when area equals 0, temperature equals 0, and precip equals 0. So when all of our x values equal 0, all of those other betas are going to cancel out, and all we're going to be left with is beta 0. And the interpretation of that is the expected number of species when all of our covariates equal 0. All right, let's move on. How about beta 1? What is the interpretation for beta 1? And that's related to area. The interpretation goes, all else being equal, that means precipitation and temp. If those are set equal, then the expected number of species increases by 0.00003855 as area increases by 1 unit. The units here are square kilometers. You can see why this is so small, because our units are so small. Square kilometer in a state is tiny. But if we increase an area by 10,000 square kilometers, then we're going to increase the number of species, the expected number of species, by 3.8, almost 4 species. That is if precipitation and temperature is held constant. So what is 10,000 square kilometers? Well, that's 100 kilometers by 100 kilometers, 100 kilometers on each side of that box. So that's not huge. So if you increase it by 10,000 square kilometers, you can expect an increase in about 4 species. How about temperature? Same interpretation. All else being equal, the expected number of species increases by 4.09. We see that number right here, 4.09 times 10 to the 0, as temperature increases by 1 degree Fahrenheit. So as we're increasing temperature, the number of species are increasing. As we go south in latitude, the number of species are increasing. That's quite a bit. If you increase temperature by 1 degree, the expected number of species increases by 4. And precipitation. All else being equal, the expected number of species decreases by this shouldn't be in here, because that's 2 negatives equals a positive. Decreases by 2.450 as precipitation increases by 1 inch. So as precipitation is increasing, the number of species are going down. Okay, we have 4 minutes left. Let's write out what our fitted model statement looks like. All right, so we can start off with the top. Our response variable, y, I, and this is number of species, equals beta 0, our intercept, plus beta 1 times x1, where x1 is, let me go back and make sure I have the order right. X1 is area. Plus beta 2 times x2, and x2 is temp, plus beta 3 times x3, where x3 is precip, plus epsilon I, where epsilon I comes from a normal distribution with mean 0 and variance sigma squared. There's another way to write this, and you'll often see this in journals like the Journal of Wildlife Management or Ecology. And what people do is they take this value and plug it in for x1, just so you know exactly what you're talking about. So if we did that, it would look like this. yi equals beta 0 plus beta 1 times area plus beta 2 times temp plus beta 3 times precip plus epsilon I. So we'll use both of these. What this does is it allows us to know exactly which beta 1 goes to which with just looking at it quickly. So either way of writing this is fine. This would be more of a general way of writing it that applies to all situations. This is more of a problem specific way of writing it. And then we would need, don't forget epsilon I is normal. Mean 0 and variance sigma squared. Okay, and the fitted model statement, this is the general model statement. The fitted model statement, let's see, I have 1 minute. yi equals our intercept 184.1 plus 3.855 times 10 to the negative fifth times temp plus beta 2, which is 4.095 times precip plus, going down to the next line, plus negative 2.45 temp, I forgot area. Trying to do this fast, temp, precip, plus epsilon I, where epsilon I comes from a normal distribution with mean 0, and then the variance is 45.51 squared. So that's our fitted model statement. General, fitted. And this would be the model if we use this model to make inference. Okay. 9:50. I'll stick around on here until office hours if there are any questions. I do have office hours at 10. Thanks, everyone.
Have a good day.
You too.
I just have a quick question. I just wanted to confirm that the lab isn't due next week because of the holiday. It's due the week after.
Yeah, Monday's lab will be due the week after. So Monday, Let's see. I hadn't thought about that. Let's put every lab 2 will be do the following. So you have 2 weeks to do lab 2.
Okay, and so if we have lab on Monday, you don't expect us to show up on Wednesday or anything like that?
Wednesday, well, right. Yeah. It'll just be lab. The Wednesday lab's going to be leading the charge.
Okay.
So it's going to flip because there'll be another flip later in the semester and it'll go back.
Okay. All right. Sounds good. Thanks.
Yeah. So Wednesday you'll see the material first, starting Wednesday. So Wednesday there is lab. Monday there's not lab. And it works out. I think I don't remember which holiday is on Wednesday, but Dead Day or something.
Professor, can you hear me?
Yeah, I can hear you.
So for the lab, were we supposed to use the information that you just provided in lecture today? Because I started it and I think I did it all wrong because I didn't know that it was supposed to be done that way. So I don't know if I can share my screen with you. I'll try.
I have to let you. Let me find you on here. So you did not need the information today, except maybe I gave an example of how you read in the data. Let's see, I don't see you on here. Shane. Oh, there we go. Okay. Okay, you can share your screen now.
Okay. Let me do that. Hold on 1 second.
This is one of the benefits of online course versus in person, because unless you had a laptop, you wouldn't be able to show me exactly what you were doing.
I don't know if you can. Oh, wait, hold on. There we go. It says it's loading.
Okay. The only thing you would have needed from today's lab, because lab 1 doesn't touch on multiple linear regression yet.
Yeah, I was talking about this lab 2 because I was part of Monday's lab session.
Lab 2. That should be multiple linear or simple linear regression still, right?
I think so, but it used the same Excel data that.
Oh, right. Yeah. But it's still simple linear regression. It does use the same data. That's right.
It's taking so long to load.
Yeah, so today, the difference between lab 2, and today, in lab 1, you only fit one of those covariates at a time. You don't do x1 plus x2 plus x3. You just do y tilde x1, then the next one is y tilde x2, and then the next one is y tilde x3.
I don't know if you can see that or not.
Not yet. There it's starting.